Hi guys, what's up? This is Dr. Aeronautics, and today we are going to the beach. We're going to Brighton Beach. I don't know if I'm pronouncing that right, but I'm sure you moon junkies already know where we're going. For you who don't know, we're going to the moon. I'm serious. We are actually going to the moon. I have gone through just about everything you need to know to fly a moon flight, and we're going to put it all together today. So you're going to see a complete flight from the ground here at Cape Canaveral to the fictional touchdown pad at Brighton Beach on the moon. It's a crisp, clear day. Well, it's probably hot and stuffy here in Florida. So, never mind. But the great news is, if you thought 80 degrees wasn't hot enough for a nice beach vacation, Brighton Beach is probably, don't know for sure, but is probably about 250 degrees Fahrenheit. So there'll be plenty of sunbathing in all spectrums. But enough joking around. This is a very serious mission. So we're going to get started now by closing the cabin hatch.
Hatch closed.
So you say, creepy computer voice. Okay, I actually like it more on the XR2 because the XR2, they actually got a famous person to do the voice recording. And it's all fancy, so it sounds more like a limousine talking to you than one of those creepy computers. Okay. Let's power on, and I'm going to get this right every time. MFDs. So we're going to put this one onto the map. Why does Hannibal keep getting targeted? I had to keep on deselecting it. Here, watch. If I go to orbit and then back to map. See, Hannibal keeps on getting selected. I don't know why that is. I guess it, needs a base or something. Okay, so we're going to configure this one for moon flight. We want ecliptic in this case. And I'm not going to explain why for now. But we're also going to change the projection to the ship. And we're going to change the distance to that altitude. Now, we're going out to the moon, which is going to be a transfer orbit. This is our orbit around the Earth. Look at how far the moon is out. I'm going to enter the moon's orbit into this database, and you will see how far the moon is out. You can't even, well, if we, that's what I wanted to do. You can't even see the Earth. It's so far out. But this is basically the moon's orbit. If I change the projection to the target, you can see the moon is actually in an egg-shaped orbit. And we have to get out to this orbit to reach it. So my guess is when we get close to it, it'll be almost at the highest point of its orbit, which is the apogee. But for now, we're going to deselect our target and then change the frame of reference back to, or the projection rather, back to the spacecraft. And, of course, we want altitude readout before. We're going to change that later on. Turn the HUD on to surface, and it's daytime. So we're going to go ahead and get that right, and configure to the red HUD that I like. And we turn the air flight control surfaces on, pitch up an elevator trim, turn our lights on, and we should be ready for takeoff now. Okay, so now what we're going to do is figure out when, I'm going to turn that off for now because it's irritating me. We're going to find out when we can go to the moon. So here's what we need to do. Like with the ISS, we need to enter in something for the aligned planes. Oh, whoops, I didn't see that was popping up there. We want the moon. Okay, and it's giving us a relative inclination. again, we're going to do the exact same thing with the other one and count down. Try and get the relative inclination to count down as low as we can. And for the target, we're going to go to the moon. And then we get this, which doesn't help much. So then what we have to do is we need to change the, there it is right there. Change the orbit line from ground track to orbit plane. That shows the plane rather than the area of ground that the moon is going to travel over, which helps. And now you can see the moon is now a sine wave. And it's kind of inverted. It's actually like ours is a cosine wave and it is more of a sine wave. But because the Earth rotates under the plane, this line will shift west. So how do we know when to take off? Well, if we're lucky, the plane will directly cross us, and then we can just go due east from there. And we'd be super lucky. Unfortunately, that also means we're going to be taking off about 30 minutes after sunset, which is unfortunate, because I like taking off and landing during the day, because the color of the sky that you see up here shows relatively the amount of air content above you. So I know when the sky goes dark, then I'm getting closer to space. Okay, so we're going to go ahead and fast forward until that time now. 10x, 100x, 1000x. And we may, I think we are going to use up to 10,000x because the moon is very far away. It will take us about 3 1/3 days to get there, as long as nothing's wrong. Yeah, so the sun is going to set. And basically what we're going to do is we're going to wait for, you see that ridge right there. We're going to wait for that ridge to cross us. And then we're going to head directly east. And then if we're lucky, we'll only have about 6 degrees of inclination with which to make up as a planar alignment burn. Those burns that I hate. So we're going to go ahead and wait for this to get very close, but not exact, because we want takeoff time. Okay, 10x, real time. Okay, so the sun has just set, and the stars are beginning to come into view. You can see Venus is still there, and this is actually where the sun position is under the horizon. Some of the more brighter stars are starting to appear, so this makes for a good twilight takeoff. Let's let's not revert yet, and I'm also going to keep us zoomed in to the 16 level, so that we can basically hear, actually there's no need. All we need to remember is we need to launch due east within the next few minutes. So I'm going to go ahead and zoom us in there, turn the HUD back on. And unless I'm mistaken, we're ready for takeoff. So, we're going to turn due east. I'm actually going to wait a few more seconds on the pad and pause the video momentarily while that happens. Okay, the time is now. We are just under 6 degrees relative inclination, which is what I was hoping for, and now we launch about 89.9 degrees about to the east, just barely northeast, but as far as we're concerned, it's east. So we're taking off in 3, 2, 1, applying
10,
full power.
9, 8, ignition sequence has started. 6, 5, 4, 3, 2, 1, 0. We have commit and we have liftoff.
We want to go to the surface. Okay, there's rotational velocity. And like always, we're going to go ahead and cut back on the throttle, gear up. And we're turning as fast as we can eastwards to
30,
90 degrees.
gear up. 20,
oh my god.
10.
Oh my god. I think we just barely touched the wing to the ground. Yeah, I think our wing just barely touched, but nothing seemed to happen. Our gear was up, and I heard the little bit of the boop from rubber hitting the ground. So I think we literally just scraped the top of the grass. If something worse happened, we would definitely hear the crash sound. That was pretty close. Okay, so here we are. We're applying full power now. We're going to accelerate out of the atmosphere, pitching up to 30 degrees as normal procedure dictates. We're going to advance out of the horizon indicators here. And we're going to keep an eye on the planar alignment. We want to try and get this rate to stay at 0.00. If not, then we're doing something wrong. Yeah, so we want to actually be at 90 degrees here. That's one of the reasons why it's not perfect. Just using a little bit of RCS thing to balance that out. So next level up, we're at about 22,000 feet and 640 miles per hour. About 30,000 feet now. Coming up on 700 miles per hour. Okay, so we're all set with a planar alignment, so we'll just keep an eye on this. And of course, as the air is getting thinner, you're noticing the pitch down, which happened in all of the other tutorials. The plane appears to be torquing to the right. I'm not sure why, but we're going to have to counteract that. Just about 1,100 miles per hour now. Maybe a little bit faster than that. We're about 60,000 feet now. So for fuel saving, I'm actually going to throttle down and use the scram engines to accelerate myself along, because we want to try and save as much fuel as we can for the moon. It won't be able to do all of our work, but it can do most of the work. Or not. But the scram fuel is useless unless we do something with it. Going to the next zoom level. We're now at about 75,000 feet, and hang on a sec. No, that's about 85,000 feet, and we're now at about 2,500 miles per hour. You have to be using a little bit more gas here. Now, as we go downrange, our direction will change because of gyroscopic precision or whatever they. No, that's something else. It's the frame of reference, so that's normal actually. Oops, plasma cloud. That's not. Okay, we're all set. The scram engines are working now at full capacity, so I can turn the engines off. Going to start relaxing elevator trim. 100,000 feet, 4,500 miles per hour. Okay, there go the scram engines again, so we're going to have to start using fuel again. We're at about Mach 7, which, as I recall, was the upper limit of the operation of the scramjets. Yeah, it is. It's kind of stupid because they wouldn't be like this in real life. Another reason why I don't like the Delta glider as much, we're going to actually have to use more fuel now. We've topped out about 110,000 feet, and we want to keep going. Again, 60 kilometers is what we're aiming for. And now that we're at 110,000, we'll go ahead and switch to orbit. Okay, scramjet is done. So it's off, and we're back to full power. I don't think it's possible to do a fuel dump, which kind of sucks, because this is just going to be dead weight sitting in our tanks that we're not going to use, and it's just going to be sitting there unnecessarily. Oh great, not again. So we're going to pitch up, vaulting us out of the atmosphere, because the high dynamic pressures are not good, and I'm actually going to keep a closer eye on that. It should be below 10 by now. Alright, we're at approximately 7,000 miles per hour and about 140,000 feet. So the dynamic pressure is more under control now, so we're going to go ahead and stop us from going too high so that we can recall some lift as we accelerate. Not that far now. And we can go back to the map now. Okay, because our orbit's developing now, we can change back to the orbit plane. And you can now see our resultant orbit plane as with the moon. And you see here the paths cross. This is the node. This is going to be the descending node. We're going to do an orbit plus burn right here. Yeah, I thought I heard that. Oh, in fact, we're going down again. I'm going to go ahead and drop the raise the elevator trim. We're now at about 9,000 miles per hour, and about 150,000 feet. Yeah, so we should be moving way higher than this right now. We're actually wasting fuel because of it. So anyway, this node right here will happen, and we do a planar alignment burn right here. Those planar alignment burns, which I don't like because they're rather expensive. Okay, now I need to control the slope again. Now it's gone silent. That's what I want. about 11,000 miles per hour now, and this is the last altitude call out that I'm going to give. We're at about 190,000 feet. I typically stop giving thousands of feet call outs at 100,000. So you lucked out. So because we're not staying in the parked orbit or looking for a low Earth orbit, we don't need to be concerned with our apogee altitude. So we can use any altitude we want. But for the sake of orbital checkout, I'm going to cut the main engines as soon as we reach an apogee over 400 kilometers. Okay, now this is right where I want to be. We're at 6,000 meters per second, entering ballistic trajectories now, and we're just now topping out, which is exactly what I want, because the slope will change as soon as we start to reach orbital velocity. And there you can see now it's increasing. That is precisely what I wanted. So it doesn't get any better than this. We literally have maximum efficiency. We're at full fuel, the precise target altitude in the precise direction at the precise time, with hardly any dynamic pressure. This is a perfect ascent right now. Do I hear the atmosphere again? No, I don't. Yeah, sometimes you just hear weird things in the space plane. You'd be flying along and you'd be like, is that a washing machine draining? It's just the repetitive noise makes you hear things that aren't actually what's the word for sounding? That aren't an actual truth sounds, I guess I should say. Okay, so we're now reaching orbital velocity. You can see our apopsis increasing now to 200 kilometers now. And we're very close now. Here's Miko. Okay, so I can hear a little bit of atmosphere. So this is going to perturb a little bit because we're still rather low. But you can hear the last little bit of atmosphere is leaving for the last time because there's no atmosphere on the moon. Okay, we need to prepare very quickly now for the planar alignment burn, which is going to occur for a period of about 60 seconds when the time to descending node is 30 seconds, which means we have a little bit more than 8 minutes, so we don't need to be that quick. And it's where this crosses right here. Okay, and with that, I'm going to the orbit HUD, and I'm going off the ineffective air flight control services and turning on the reaction control system.
Rotation.
And then I'm also going to turn prograde now. Yes. And we're in space now, so we're going to go ahead and go to the green HUD. Wow, we nearly broke 8 kilometers per second here. Okay, we're now gonna actually go back to pitch now and reset the elevator trim so that we don't get torquing from the last little bit of the atmosphere. And then gonna go off again of that. And we're now in a stable orbit configuration. The last little bit of atmosphere has left us. I don't hear anything, so I'm going to go ahead and deploy the radiator. Which is, again, to cool our system, since radiation is the only way for the spacecraft to cool.
Radiator deployed.
Okay. We're all set. So now we're going to keep an eye on this. And I'm actually going to go off of prograde now. I'm not going to turn until we get really close to the node. Because we're still very low in altitude, and when we turn upwards, it's kind of like pointing, it's kind of like making a paper airplane and then throwing it from where you hold it forwards. It just doesn't go anywhere, because it's like it's like sticking a cutting board out the window, and you feel it on your hand. It's very inefficient. So we're now at 10x. Okay, now it's time. We're at about 180 kilometers, which should be high enough. Hey, and look, it's the moon. That's where we're going. It's right there in front of us. But, like in the joke that I made earlier, though it may be in front of you now, my first tutorial, which was not really a tutorial, it's just a fly straight to the moon. You could see that it would be very inefficient if at all we reach the moon. So it's just a happy coincidence that right now it's visible out the front. So that's pretty cool. Right. We want to look at the map. And when these two lines, we're trying to get these two lines here to converge. And just so I don't mess it up, yes, I have it correct. I would confuse myself earlier with which direction it's going to be, whether it's going to be up or down, depending on whether you want the node to go more inclined or less inclined. Okay, here comes the burn. 3, 2, 1. And there you can now see it says to engage the thrust. So we are thrusting right now at maximum power to try and get these two lines to converge perfectly. It matters. If we don't get them to converge perfectly, we won't get to the moon. It's that important. Okay, I caught the end of that recording just in time. Not sure if you heard it, but we need to get this to 0. If we don't get it to 0, we will not go to the moon. It's that important. Okay, here comes the end of the burn. 0.5, 0.4, 0.3, 0.2, 0.1 now. Perfect. I really like it when you do this for a while, because you get an idea for just exactly when you cut the engines, and I think I cut it perfectly there. Turning prograde again because we're still low in altitude and I don't want to cause a drag force. And now you can see our lines here, our orbital plane lines, coincide with the moon, which is what we want. We can go back to the ground track now. Okay, so the next thing that we need to worry about, that's a favorite number of mine, 7765. I have many of those. By the way, 17,600 miles per hour, about, I would say. 7,760, that's another one of my favorite numbers. We now need to be concerning ourselves with the departure phase. So this is the transfer MFD, and it's useful when you're trying to go to a moon. Look at that, 0.00. You can't ask for anything better than that. And it will perturb. So we're going to have to deal with that later, and I'll explain that when it comes. Okay, so transfer is useful when you want to go to the moon. I am not going to do the calculations now. That will go there because it's rocket science and it's astrodynamics and it's crazy. It deals with adding of orbital energies and angular momentums. But I will do the calculations for the Norsden Land Tunisia series. When we go to colonize the moon, I will do every calculation by hand. And I won't include them on the video. I'll just show you the paper that I wrote on it. A picture of that. Okay, so we start by targeting something. We're obviously going to the moon, so we target that. The next thing it's going to tell us is that there's no intersection. So what we have to do is increase this delta. Actually, no. We first do a hypothetical transfer orbit, which is right there, that basically says, okay, well, let's say hypothetically I added a whole bunch of delta velocity. That is, I sped up, so I escaped the gravitational pull of the Earth and went way out from where the Earth is. That's what we're doing now. So we have to tell it, hey, we're going to add a delta V. We're going to add a delta V enough so that we get out here. And this is a boring part because this number, as you see the delta V right here, it increases at that exact speed. And I had to hold it down until it says about 3.12. So you can see I'm only halfway down holding it now. And this is a lot like the sync orbit, except this is better when you're doing a very high altitude thing. Like, you can't really even see the Earth at the center here. The moon orbits that far out. And where is the... Ah, there it is, by the way. Next to Mars, which is pretty cool. So that's the moon. And judging by the surface, I would say yes, Brighton Beach is probably about 250 degrees. Okay, there's 3.12. So now here's what we do. Basically, this is telling us the gray line, that's where we, the green line here, that's where we are now. The gray line is where we cross this gold line, which represents the orbit of the moon. This dashed green line represents our orbit after we've done the transfer burn. And the yellow line represents the location of the moon, and the yellow dashed line represents the location of the moon when we cross the line here. And now you're thinking to yourself, oh no, guess what that means? Because we meet here, we have to wait nearly a whole month for the moon just to get around here. Well, the good thing is, we're orbiting the Earth right here, which means in 45 minutes, we go to the other side of the Earth, and then we burn this way. Uh-oh. So you know what that means? All we have to do is just leave at a different time. So this now is going... actually, no, it's not going to be the time we leave. This here is going to be the time we leave. And we don't need excess delta V. Whoops. So I'm only going to do what is required. And let's see if we can get these two guys to meet. There we go. That is it. Oh, shoot! Wait, what? Oh, wait, no. Never mind. I was about to say, wait, Is it still recording? Okay, that's kind of irritating. How this keeps on disappearing on me. I was confused as to my position. I was about to say, wait, that means I have to burn now, but no, because I'm here. It's beginning to really annoy me how this keeps on disappearing, and I've lost my timer, so I can't use it. Right, so the next thing we need to do is figure out when we do the escape burn, which, if I'm not mistaken, whoops. I can't recall if this is the distance until ejection, or if it's the distance until when the ejection burn starts. I'm not sure. But either way, it's a waiting game now. So we can go off the prograde autopilot. The planes are not going to change. So we'll... It appears I need to do the burn where I intersect the ground. So we need to do a circularization burn first. For that, I'm going to stay prograde, and we're going to accelerate a little bit. So here's 10x. And we're just going to go around it. Meanwhile, dawn should be coming up soon. We're over Central Africa. Right, so Kenya is there, which means Somalia is probably there. I saw South Africa down there. Forget what's here. Oops, don't want to spend too much time outside. Okay, now check this out. We go to the window here and take a look out it. Hang on a sec. The moon is out the window. That's really cool looking. 10x again. Here's sunrise. Okay, we're real time again. I'm going to burn until we're circular. So that should only be about a 15-second burn. So I'm going to go ahead and activate the engines now. Even less than I expected. Not a problem. And we don't need to get it perfectly circular. There's no reason why we would need to. Okay, we're nearly circular anyway, so it doesn't really matter. But our, oh my gosh, it disappeared again! Right, so then, like it or not, I need a timer. 1 second. Okay, so I have a timer now. And, hopefully it will work. But anyway, we need to change our, things again. We're still paused. Because... There we go. We changed the orbit a little bit, but we're all set again. So, now it's just waiting again. So, turning off prograde. And, going to, 10x now. And, we'll get a Nice video of the Earth going by as we wait. So we're over the Indian Ocean right now, and we're about to be over Australia. This is too slow. We're going to need to go up to 100. So there's Australia. That I think was New Zealand. Okay, what I need to do now is figure out when, if this is the time until I'm here, I need to figure out the time that I need to start my burn, just in case that's not the burn start time. Okay, so I need to start the burn 85 seconds before DTE, and by that time we will be able to figure out which one it's talking about. Also, as expected, we've been perturbed. We're actually at a node right now.
Translation.
So we can fix that right now. Oh, what the... Here we go. Actually, better yet. We'll just use the hover engines. There we go. And that's going to perturb more, but I'm fine with that for now. Right, so we're coming back over North America again. We're also going back to 10x to get to our burn time. Okay, burn starts now if that's the time until this thing. So I'm going to hope it is. If it's not, our burn will be off, and then we'll have to fix it later, which sucks. There really needs to be a fuel dump for the scram. I'm actually legitimately concerned now that we could run out of fuel. And That's not even, like, I'm concerned, and then I'm concerned, and then I'm concerned. I'm the third concerned now, which is not good. And because the Delta glider doesn't offer any bit of accessories, I can't do anything about the fuel. Whereas if I was on another mission, I could either do a rescue mission, or I could take out the emergency fuel supply that's located in the rear vestibule, that kind of thing. Plus, it's also a tutorial, so if I run out of fuel, it sucks, because then it's not a beginning to end kind of thing. It's broken in the middle by you magically cheated to get more fuel, which is a problem. Okay, so the time till ejection thing, it was indeed for the line here, so we did begin the burn at the right time. Or at least I think we did. What's the acceleration here? Oh, shoot. No, I actually began it late. I thought we would have more acceleration than that. Let's see, it adds a little bit. I'm also translating to make up for the lost time that we spent doing that. Now you can see our burn here developing. If I go to the orbit, this is where most of the stuff is happening. You can see now our orbit is way perturbed. Look at the, we're switching now to radius 178. Oh, we're coming up on it now. Throttling back now. There we go. That was a good ejection burn that nearly matches the hypothetical transfer here. That's perfect, and the relative inclination is low as well. We still have plenty of fuel left, which is good, but look at how high we're going now. 438 megameters. That's insanely high. So now that this is no longer hypothetical, we click HTO to take it off, and that's our new orbit and case. So now we can switch back to orbit, and we can switch this other one back to the, what is this? Sync. No, transfer. There we go. And you can see already we're going faster than 10 kilometers per second now. We've nearly ejected from the Earth. We have nearly ejected from the Earth, and you can just see our speed is increasing very quickly. Oh, where's this? Puerto Rico. I was about to guess that. Now that's cool. Check it out. The eastern seaboard, everyone. All the way from Key West to Boston. That is cool. It's actually the last time we will see the eastern seaboard up close. Because we're going out to the moon now, which is now in front of us, and it's in front of us for a reason, because we're going there now, but it's not totally in front of us. as you can see now, the Earth has now dropped from view as we are now at 670 kilometers in altitude. We can see a lot now. We can see just about the whole of the Atlantic Ocean now. As you can see, look at how large our horizon marker has gotten. So we've just entered what's called the cruising phase of the flight. So I'm going to go back to rotation, and I'm going to go ahead and take it off the ProGrade autopilot. And I'm going to go to 10x time acceleration because we've entered cruising phase. So here's 10x. And we're just going to watch the Earth slowly drop away from the spacecraft. Just at about 2,000 kilometers altitude now. That would be Brazil. And so now the first things that you begin to notice as you drop away from the Earth is just all this empty space, like before we were near the Earth. And then there's just all this crazy empty space like all around us. And that's why they call it space, is because that's literally what it is. It's nothingness. And speaking of vacuums, we've nearly doubled our altitude, and now we're going to check out what the atmospheric pressure is. Is that even possible? Yeah, atmospheric parameters are gone. So, oh my gosh. No, that was very bad. That was very bad. That was very bad. I accidentally hit, oh my god. I accidentally hit the engines while we were in 10x. A waste of fuel and very bad. I'm going to have to lock the joystick while we're in motion. We need to go back to the transfer orbit. Oh my god. Yeah, we've messed it up. We need to do a retrograde burn now. This occurred when we were at 353 plus 180 would be 70, 73, 173. We need to do this as fast as possible. All this time, and I still haven't gotten used to the engine power of the RCS. Now what happened? Man, all these glitches are concerning me. Okay, but we've managed to save it, and we haven't wasted that much fuel, which is good. 6,000 kilometers. I'm going to go ahead and advance, well actually first I'm going to turn ProGrade again. I'm going to do this on 10x so that the tutorial isn't too long. And we're going to continue from here on 100 times acceleration. Also, the final sunrise over the Earth is occurring now. 6,000 kilometers. We are now one radius out from the Earth. That means halfway from the Earth's center is rock, the other half is space. So here's 100x. Okay, I've moved the joystick so we shouldn't have that problem again. That is Madagascar and Africa. So this is what inspired the Apollo astronauts. Let me turn this off now because it's getting repetitive. And now you can hear the true silence of space. So this is what inspired the Apollo astronauts about the blue marble picture. As we drop away from the Earth now, you can see it is literally a ball in space. And, you know, that sounds corny sometimes, but it's the truth. It's seriously the truth. And it's fantastic at that. And there's the sun, which is now very, very much more powerful because we're far out of the atmosphere. There's no air. Whatever air we have around us now is because of solar wind. There's the moon, still looking about as small as it was when we left. That's because we haven't gone very far. But we're going to increase now. We're at 55,000 kilometers now. We're beyond geosynchronous. If we look back to the map, our ground track is going haywire along with the moon now. So I'm going to go ahead and advance us to 1,000. Times the normal rate. There we go, transfer. So here's 1,000 times. I'm going to let us spin because it just kind of gives a nice tour of space. So you can see the gas giants Jupiter and Saturn there. You can see now the Earth is rotating. It's really far away now. And look at the orbital speed. It's coming down. It was 10,000, now it's 2,000. That's because the gravity of the Earth is getting weaker, and we're staying in orbit even though it's this. Also to note, look, the G value is decreasing. This means that 75% of the gravity we feel right now is from the Earth. Can you guess where the other 25% is? Believe it or not, it's not the moon. It's actually the sun. If I show you here, still on 1,000 now, if I switch to, also we're a third of the way to the moon, if I switch to, actually I'm going to go back to 100 times because of the, we're getting closer. If I switch to the moon, you'll see only like 1 or 2% maybe. Wait, what happened? Oh wait, I targeted the moon. That's not what I wanted to do. I wanted to reference the moon. Yeah, 0%. See, even less than I expected. And the other 32% is from the sun now, only 68% from the Earth. Yet we're orbiting the Earth because we're going about the same speed together around the sun.